A lot of you have raised the question about logistic regression is on the homework, and actually not on the online questions, but it's on the homework. And there are some topics like bag of words, which is in the online questions that we haven't covered in class formally. But bag of words will actually be covered in the recitation. So actually, I wanted to start off by reminding you of the recitation tomorrow. Nicole is going to do it, and it will cover essentially Gaussian naive Bayes. So if you remember in class, we talked about naive Bayes, and we talked about discrete features, right? So we talked about the MLE and the map estimate when our features are binary, right? That's an example of discrete features. Your features could also be modeled by a Gaussian distribution, and in that case, it just becomes Gaussian naive Bayes. So it's a really simple putting 2 and 2 together. We already talked about Gaussian Bayes, and we talked about naive Bayes in the discrete setting. If you just put them together, you get Gaussian naive Bayes. So Nicole will be talking more about that. And also, how do you get, we derive the MLE and map for the Bernoulli model. How do you do it for the Gaussian model? Okay, and she'll talk about that as well. And then the bag of words approach, which is basically an application of naive Bayes to text classification. Okay, under this special model that she'll talk about. So strongly encourage you to attend that. It's again tomorrow, 5 to 6:30 in the same room. Okay. And yeah, we do apologize for a slight change in the order. We were hoping to cover logistic regression last time, but I've been having a very bad throat, so Geoff was courteous enough to actually move the Perceptron class up front. So we did a brief intro to Perceptron. We'll go back to the analysis of Perceptron, but first we'll talk about logistic regression. Hopefully my throat will work through. People in the back can still hear me? Good? Okay, great. All right, so let's actually go ahead and talk about, you've seen 2 classifiers so far, right? You've seen the, or I should really say 3 if you want to count Bayes optimal classifier and the naive Bayes as 2 separate classifiers. We have seen those 2, and then we have seen the perceptron. And we'll talk about yet another one today, which is logistic regression. Okay, but I wanted to sort of first talk about this more higher level classification or categorization, I should say, of classifiers into generative and discriminative classifiers. Okay, and the classifiers you have seen so far can be grouped into one of these. Right? So generative classifiers are, for example, naive Bayes or even Bayes classifier, where you assume some functional form for how your data was generated. So the data is both features or inputs, and then your labels are the outputs. And if you come up with a joint model, so if you assume something about P of x and y, which you can do in many ways. For example, you can, the way we did it so far was we assumed a class prior, and we assume a class conditional density P of x given y, right? You assume a model for both of those. You plug in your ML or map estimates, and you get the corresponding rule, right? So you estimate parameters, whatever are the parameters in your class conditional or the class prior. So if your class conditional density is just something like Bernoulli, then you'll plug in the MLE estimates, which is this fraction of the count, right? Relative count of that particular value appearing. If it's Gaussian, then as you'll see, you plug in the corresponding estimate of the Gaussian parameters, which are the mean and the variance. And finally, what's the rule? The rule is that we want to output the class for which the product of the class conditional density and the class prior is maximized, right? This was our the optimal rule. And for naive Bayes, this term just factors, the likelihood just factors over the features. And you can see that, in fact, the very first class when we derived the Bayes optimal classifier, we actually wrote it as it's the class that maximizes P of y given x, right? So you might wonder, why do we have to go through this hoop of trying to first estimate P of y and P of x given y separately, and then try to come up with the rule? Why can't we just assume a model for P of y given x directly, right? That's a natural question to ask. And this is exactly what the discriminative classifier approach gets at. So generative classifiers say we want to model how all of our data was generated, the inputs and the outputs, and that's why you assume models for this and this, right? Discriminative classifiers, on the other hand, say, can we directly tackle P of y given x? Okay, so why not learn P of y given x directly, or better yet, why not just learn the decision boundary directly? And that's really what, so you saw an example of a classifier last time where we were not modeling P of x given y, P of y, or P of y given x, right? What was the perceptron going after? Say that again? Decision boundary, right? It was directly trying to say that our decision boundary is a linear, is a line, and let's learn that line, right? Using whatever margin criteria and so on. So we were directly trying to model the decision boundary. Okay? So you can think of many approaches you can take. Generative classifiers assume model for both x and y. Discriminative classifiers either directly try to model the boundary or try to assume a form for P of y given x directly. Okay? And we'll see that this leads to different rules, even if your final decision boundary might be of the same form. All right. So this is not working because I haven't connected it. All right. Okay. So you've already seen one discriminative classifier, which is Perceptron, and we'll be talking about another one, which is logistic regression. Okay. So Perceptron was an example where we modeled the decision boundary directly as a line. Logistic regression will try to model a form for P of y given x. Okay? And then the idea is similar, that now we'll assume some functional form for P of y given x, and we are going to estimate the parameters of this P of y given x form, all right, directly from the training data. So what does logistic regression assume? It assumes the following functional form for P of y given x. It's 1 over 1 plus e raised to the power of a weighted combination of your features, right? So this is nothing, this is very similar to what you saw for Perceptron. It's just a weighted average of all your features. And even there was this W naught weight, which was a constant, but you could think of your first feature as just being 1, and then you can just think of this as a weighted combination of all the features, including 1, right? So now this is saying, let's take that linear form and make it into this 1 over 1 plus e to that linear form. Okay, so why might we assume a form like this? Because if you look at what this function is, this is called the logistic function. If I just look at 1 over 1 plus e to the minus z, then that's called a logistic function or a sigmoid. And you will see it appear again and again in this course, in particular when we'll talk about neural networks or their more advanced form, which is deep belief networks. Then again, this logistic function is going to appear. So it's essentially a transformation. In the case of logistic regression, what it's doing is taking a linear combination of your input features and transforming it into this form, 1 over 1 plus e to the minus c. How does this function look like? So if we plot this logistic function as a function of its argument z versus z, you see that it has this nice shape. Some good properties about this shape is that it lies between 0 and 1, which is needed because we want to model probabilities, and they have to lie between 0 and 1, right? And it says that when the argument, which is z or minus z here, is 0, when this argument is 0, the value of the function is a half, right? So it's saying when the weighted linear combination of the features is 0, the probability of y being 1 is half. What does that signify? If probability of one label is half, what's the probability of the other label? It's also half, right? So both labels are equally likely to happen. And when does that happen? At the decision boundary, right? So essentially what this is saying is that for points or for input features for which this linear combination is 0, you get the decision boundary. Those points lie on the decision boundary, and for those, the corresponding probability is a half for each class. So each class is equally probable for points that lie on this, essentially this line when this thing is equal to 0, right? That's a line if I set this thing equal to 0. So what is the decision boundary that logistic regression is going after? I just told you the decision boundary is the set of points for which this quantity is 0. That's just a line, right? You saw it last time. So even logistic regression, just like Perceptron, is actually trying to say that your decision boundary is a line, but it's not directly modeling it as a line. It's modeling it through this form for P of y given x, right? But that's why both of these are discriminative classifiers, because they directly try to discriminate your labels without caring about modeling how your data might have been generated necessarily. They're not modeling how the features might have been drawn for each class. So no model for P of x given y. And you will see that that's actually important when we are going to try to train this classifier. Okay, we'll have to come up with a slightly different strategy. Okay, so back to the logistic function. So now we understand that when this argument, which is the linear combination, evaluates to 0, the probability is a half. When it's something large, the probability goes to 1. And when it's something negative and large, it goes to 0. Right? So you should just think of this as the probability of y is 1 given x, and it's saying it kind of behaves like a nice curve. It's 1 on one side, on one end of your, so if you're thinking about distance moving away from that line, on one side it's 1, on the other side it's 0, the probability of one class, and at the boundary it's equal to half. Okay? So this transformation is actually a very useful tool. It's used very often whenever you have an output that's a real number and you want to convert it into a probability. Because you can plug in any real number here, z, and what it gives you back is a number between 0 and 1. So it's a way to take a real output and convert it into a probability. Okay? So another difference you can see here compared to Perceptron, both are going after linear decision boundaries, but logistic regression actually gives you the probability for a class. It's not just saying that a particular input should have this label. It's actually telling you what's the probability of it being that label. Okay, so that's the difference. If you want, in many applications, you might actually want to output a probability, not just output what the label should be for that class. All right, so logistic regression gives you a way to do that. And one other point is that for the naive base, which was a generative model, we actually had to come up with different strategies, right, to talk about discrete features versus continuous. So discrete being the binomial ones or Bernoulli ones that we talked about in class, and continuous being modeled by the Gaussian distribution, and you have to use a different MLE map approach to plug in the estimates. But here, these xi's could be discrete or continuous, and we are going to use the same method to train this classifier, no matter whether the features are discrete or continuous. Because we are not really modeling. We are not saying how the x's were generated. We are not assuming a model for it. So we don't have to do different estimates. Okay. So what are the parameters of this, this model that logistic regression assumes, which is on P of y given x? It's just the weights, right? So you have, how many parameters do you have? If there are d features? D plus 1 generally, yeah. So 3 in the 2D case, but in general, d plus 1, right? Okay, so let's, I think we have sort of already talked about this, that logistic regression leads to a linear classifier. So even though what it says is let's assume this form for P of y given x, if you look at the decision boundary, which happens when both classes have equal probability, that's the definition of the decision boundary, right? If this probability is higher, you assign a 0. If this probability is higher, you assign a 1. And if you, actually, you can try to do it mathematically, plug in the expression for P of y is 1 given x here, and the expression for P of y is 0 given x over here, which is just going to be 1 minus that. And you solve for it, you're just going to end up with this rule as your decision boundary. And we already talked about this, right? When we talked about the logistic function, when does it achieve value equal to half? So saying these two probabilities are equal means when is one of the probabilities equal to half, right? So you set this equal to half, that's another way to do it. If I set this expression equal to half, you see that e to the this has to be equal to 1, or the linear combination has to be equal to 0. Everybody follows this? Why the decision boundary is linear? Any questions on this part? Okay, good. All right, so how do we train this? So we said that there are all these parameters, W0 to WD, in this in the logistic regression. Now we have training data, which are sets of n instances of features accompanied by their labels. Every feature is d-dimensional, right? So sticking to our original notation. And well, you might say, let's just do maximum likelihood estimates, right? That's one thing we know how to do when estimating parameters. So what's the maximum likelihood estimate? It's basically just you're trying to find your set of parameters, W0 through WD. And you say that pick the parameters that maximize the probability of your data given under that model, right? Oops, under W0 to WD. And in this case, our data is just these X J's and Y J's, right? And because they are all IID, we assume that these are drawn IID from the same distribution. That factorizes the probability of all of the data points is equal to the product of the probability of each set of data point. Given the W boldface notation here means it's a weight vector which contains all the weights W0 through WT, right? And we can maximize this. Can we do this? How would you go about doing this? Say that again, somebody. What would I plug in for P of X given Y? X and Y, sorry. But what would I plug in for this quantity right here? Not conditional independence, but what does logistic regression assume? It assumes a model for P of Y given X, right? That's all we know. So we know P of Y given X. To do maximum likelihood estimate, we have to maximize the joint probability. That's not possible unless you assume a form for something else, right? So where's my pen? Yeah, right here. Okay. So we are saying that maximum likelihood estimation requires us to maximize this under our weight vector, right? What we have a model for is just this. So we need to multiply this with essentially P of X, right, to get to the joint distribution. But we haven't assumed anything about P of X. Logistic regression does not assume anything about this. It says for the purpose of getting to the decision boundary, all you need is P of Y given X, so Y model P of X. So you can't use the standard maximum likelihood estimation procedure. But what you can do, so the problem is that we don't have a model for P of X or P of X given Y. We only have a model for P of Y given X. But what we do is that we maximize what is known as the conditional likelihood. So it's not the same as MLE, but it's MCLE, if you want to call it that. And it's saying let's just maximize the product over all our data points of P of Y given X. Seems reasonable because that's the only thing we assumed something about. All right. So let's try to do that. And yeah, essentially, the discriminative philosophy in general is that you don't waste any effort or any data points trying to learn parameters of P of X, because all you care about is P of Y given X, right? So we are only going to work on the parameters of P of Y given X. So let's try to do that. Now, this we know how to write. We know logistic regression has a form for this. So let's write that out and see what we can, what does this maximum conditional likelihood simplifies to. So here is, I always forget to do this change, but I hope you're not confused. It is confusing. Here I mentioned P of Y is 1 given X to be 1 over 1 plus this thing. I think on my next slide, it's P of Y is 0 given X has this form. It doesn't matter because the labels you can flip. You can call the class 0, class 1, or class 1, class 0. So hopefully you won't be confused. Yeah, I always forget to make this change. But one of the classes has this form. So the other class has 1 minus that form, right? Which is this. Everybody okay with this slight change? Yes?
I have a question about it just now. So is it possible that we, based on the training data, to estimate, use regression to use other method to estimate PX? Like
estimate PX? Well, the discriminative philosophy just says that you don't need it to predict the label. So we won't waste any training data trying to learn anything about P of X, whether using regression methods or any other approaches. We just won't waste any effort trying to do that. Okay, that's the discriminative philosophy. All right, and we'll talk about some comparison of discriminative versus generative approaches towards the end of this set of slides, and also you'll get to explore it in the homework. Right? Yep. All right, so let's see that now this is the form that logistic regression assumes. So let's plug it in. to our conditional likelihood and see what's the resulting expression we get. So what we have done here, this is instead of working with the conditional likelihood, it's easier to work with the conditional log likelihood. Right? We saw this trick earlier. Taking logs sometimes helps us do derivatives and so on. So let's look at log of this term, which we earlier said was the conditional likelihood. Right? So how do I end up with something like this? Okay, let's try to do it quickly. So we are talking about now taking log of, first of all, what's the log of a product of few things? What is log of A times B? Log A plus log B, right? So that's the first step. We are just going to write it as sum over J log of this thing, right? And it will actually help us to realize that we can write both of these probabilities using the same expression. The way we do that is we are going to say probability, instead of y is 0 or 1, we are going to say let the probability y is little y, which could be 0 or 1, given x and w. I can write it as e raised to the y times, and for simplicity, let's just write sum w, I guess, yeah, xi, wi xi, assuming that one of the features is 1, right? So we don't always have to write plus w naught. Okay, this over this. So why can I do that? Does this make sense? It's a common expression because if my class little y was 0, I just end up with a 1 here, right? It's e to the 0. I get back this. And if it's y equal to 1, then I end up with the corresponding expression. So this is a unifying expression. And once you have written it in this form, now you can see that if I plug this in here, I'm taking the log of this quantity. Log of A over B is log A minus log B. So I do the log of the numerator. Log of the numerator is just y times this linear combination, and minus log of the denominator, which is this. Everybody good? All right. Okay, so now we have an expression for the conditional likelihood. Unfortunately, the bad news is that if you try to take the derivative of this with respect to w and try to set it to 0, you don't get an analytical closed form expression. It's something which involves e to the w's and so on, equal to w or something like that, which you can't solve analytically, right? So that's the bad news. However, the good news is that this function is a concave function of w, okay? So if you don't remember, how many people know what concave and convex sets and functions are? How many don't know what they are? Okay, so 2 people know and 2 people don't know. Okay, so I suggest that you should go back and revise it a little bit. We are going to, I think, have a recitation maybe covering at least.
Yeah, sure. I mean, sounds like we ought to.
We ought to, yeah. So we will try to do a recitation on convexity, and you will see it later on in the course. In fact, we will spend a few more lectures trying to talk in more detail about how you can leverage convexity or concavity of the functions to try to maximize or minimize them using optimization-based methods. Okay? So if you don't remember, at least you should know the definitions of what a concave and a convex function means. And if you don't, you should go and look it up. All right? So we'll revisit this in more detail later on in the course, but I just wanted to mention, because you will be, in your homework, you're going to try out one optimization algorithm. In this case, it's given to you, right? Basically the whole code, but you might have to write it later on. So essentially what this means is when I say that this log likelihood is a concave function of w, it means it looks like an inverted bowl. All right? So if this is w and I plot the function L of w, it's an inverted bowl. In higher dimensions, it's just literally an inverted bowl. Okay? And a convex function is a non-inverted bowl. Okay? So that's the difference. So what's the good point about it? Well, we cared about maximizing the conditional likelihood, right? So we can see that if we start at any point, we don't know what the best w is that gives us the maximum. We can start at any point, and we have to basically try to reach the top. Good thing is that there is only one top, right? If the function was instead something like this, we would be in trouble, right? It does not have a single maximum. or actually, I mean, it has a maximum, but there's no, there are multiple local maximums. So if we start at one point, the approach we can take here is we can start at one point and we can sort of try to move in the direction of actually the gradient. Here the gradient is positive, right, going up. And the gradient is negative here of the function. So we can move in the direction of the gradient and hope to reach the top. If instead you had a function like this, then you would end up with very different solutions depending on what your original point was. If you started here or here, you are going to move in the direction of the gradient and you might hit different peaks. So you're not guaranteed to reach the global maximizer of the function. But if it's concave, then you are guaranteed to reach the global maximizer using this method, right? This is only one of the methods. You'll see maybe a few more during the course of this, this class. And one of them, the one I just mentioned, is actually called gradient ascent. So using that, you can either maximize concave functions or minimize convex functions, right? So instead of a concave function, if I had a convex function, so this would be a convex function, then I can do the same thing. I can start at any, it has a well-defined unique minimizer. And I can start at any point, say here. This is my initial guess for W. And I can move in the direction of the negative gradient now, instead of the positive gradient. So I start here, I start taking, so I'm going to update my W here, 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 and hope to reach the global minimum. So minimizing a convex function or maximizing a concave function is easy. There are methods to do that, like the one we just talked about. So we can use that for logistic regression. All right? So what's the procedure? As we just said, we are going to initialize our W vector to be some random value. Okay, it could be any random number you choose. And then we are going to try to move in the direction of the gradient. Okay, so how you have, gradient is just the derivative, but now we are talking about gradient of a vector, right? Or of a quantity with respect to a vector, I should say. So W is a vector here. L of W is just some function of it, which means that we are going to talk about the partial derivative of this function, the log conditional likelihood with respect to each of the, actually that should be W naught to WD there, each of the parameters, right? And the update rule is just that. We start with some initial W naught, and at the tth iteration, we are going to change our current estimate of W, each of the weights, to move a small step size called eta in the direction of the gradient, right? This is the gradient, and we are going to take a positive step in that direction to reach up, right? That's the idea here. We start at some random location. The gradient is positive. As we move along W, the function is increasing, so the gradient is positive. And we are going to try moving along the direction of the gradient. Yeah.
If you can only evaluate the function points, how do you estimate the gradient just by taking two close points and pretending?
How do you estimate the gradient? So we are going to use our training data to do that, right? As you will see, we are going to use the training data to estimate what that gradient should be.
Another answer is we're using calculus to figure out the formula for the gradient and evaluate exactly like Aarti said at the training data.
Yeah.
But for example, we couldn't get the derivative of the last function you just showed. Right?
Yeah, so you'll see why we can do that in a minute.
Yeah, we can't
Well,
do that.
no, I just said there's no closed form expression for solving W.
Oh, we can't set the derivative to
zero, but we can
evaluate the derivative.
Right.
Right, we can't set to zero and solve, but we can write down an expression for the derivative.
Right. Yeah. And in fact, we'll do that right now. We'll try to look at what the expression is, but setting it equal to 0 does not give a closed form expression for W. All right? These are two different things. Yeah. Any other question before we move? Okay. So let's try to derive. This is known as the gradient ascent rule, but really it's just this. This is the gradient ascent rule. And if we actually compute the derivative with respect to each weight, we actually get an expression that we can plug in and write a code that can do this update for us, right? Starting with some Wi0 as our initial guess for the ith weight, and then making these updates. All right? So what does this gradient look like? Let's do that, and we'll convince ourselves that it looks like this. So we are talking about evaluating this quantity, which is the gradient of the log likelihood with respect to the ith weight vector. All right? we already had an expression for the log likelihood, right? It was this thing right here. So let's look at this expression and try to take the derivative with respect to the ith, with respect to wi. All right? What happens? So actually, yeah, let's think of this as just some wi xi, thinking the first feature is 1. I think it's helpful that way. So for the first part, in fact, maybe I can even write it here. So we are doing del by del wi of yj times sum I wi xi, right, minus log of 1 plus e raised to the power sum I wi xi. Let's take the derivative with respect to wi. We get yj times, what happens here for the first part? I just get xi back, right? The other weights don't change with respect to the ith weight. Minus, what about the log term? Log is 1 over, the derivative of the log is 1 over the expression, which is this. And then we apply chain rule. Now we have to look at the derivative of the term inside the log with respect to wi, right? And what's that going to be? 1, we just get 0. For e to the sum part, you get back exactly the same expression, right? Which is this. And then we also have the term, the exponent, and we take derivative with respect to wi of that, we get back xi, right? So what I get back is xi. I can pull that out from both the terms, times yj minus e to the sum wi xi over 1 plus e to the sum wi xi, right? Yes, thank you. Actually, I didn't write it over here. It should have been, yeah, the sum over j of all of this. Yes, thanks. All right, so that's our gradient with respect to wi, right? And as you can see, if you set it equal to 0, you're not going to get an expression from wi very easily. But we can evaluate this gradient and use it in our gradient rule. All right, so that's actually what this is. And actually, if you're clever enough, you would have noticed that this second term in the braces here, or brackets here, what is that? It's a form we have seen before, right? It's just the probability of y is a 1 given x under the logistic regression model, right? So that's why if you see here that the update rule is simply you take a small step eta in the direction of the gradient, and for the gradient what we can do is we just plug in, actually look at this expression because the first one is for w naught where xi is 1, right? So maybe you can look at this one. So we have the our xi is here times y minus this thing is just our, we can plug in the estimated probability that yj is 1 given xj, right? So in fact, yeah, if you're careful, I think I might have dropped the j's here, but they were the j's which come in because of the sum over all data points, right? So all of these had j's here. Right. So this is the probability yj is 1 given xj, right? And that's what we can plug in here. So now we actually have a very nice interpretation for this update rule. It's saying that our weight changes by an amount which is just a weighted combination of our xi's multiplied by, for that particular, for the jth data point, how far do we think the actual label is from the, you can think of that this as the predicted label, right? This is a prediction of what the label should be, or at least what, based on the current weights, what we think yj, probability of yj is. And this is just measuring how far is the estimated probability of the label being 1 is from the actual value yj. Okay? And that's how important that feature is in some sense. And we make an update. You can think of this whole thing as another weight, not the w's, but another weight on the feature. And we are making an update to our w based off of that. Okay? So any questions on this? Yeah.
So sort of here in the second formula, we're actually using data points.
Yes.
But
So-
using a data point isn't like evaluating the function at a point. That would be correct.
Well, so we were actually maximizing the likelihood of our data. So the data was already there, right? We know now that this is supposed to be the probability, right, of y is 1 given x, or of yj being 1 given xj. And we are just going to plug in the empirical probability based on data. Yeah. Any other questions? Okay. All right, so what we discussed today, this method of trying to find the maximum of a concave function using this small updates to your weight vector or the parameters you're optimizing over as in terms of the gradient is known as gradient ascent, and that's only one of the optimization methods. There are many other methods, maybe some of them we might get to later on in the course, such as Newton method, conjugate gradient descent, iterative recursive least squares, and so on, that we might see, or you can read up on your own if you are interested.
Yeah. That's the question. So it seems like you're adding something more to gradient descent here because you're not only trying a different W, you're selecting a different random data point to use in the probability function as you change the weights. Is there more mathematics?
No, you're summing over all data points rather than
overall
selecting
data
random.
points. Okay.
Right. So the objective is a sum over all data points, and when we take the gradient of the objective, the gradient passes through the sum, and we get a sum of the gradient of each individual point.
Okay.
Right. Yeah. So the sum over the data points is still there. Yeah. So each update might seem like it's, that's why I said you should think of this as the weight on the jth data point, right? On how good you are at predicting its label using the current value of W's.
Or the jth data point is coding for which direction to make the weight, right? The
Yeah.
direction that makes it more likely to be correct.
Go ahead, sorry.
Some of all data points will be very slow if you've got a lot of data points. Is it possible to like fill out points to do that?
Yes, in fact, that's known as stochastic gradient descent, right? Where you update your gradient, but only based on one data point at a time instead of the sum. If you have a lot of data points, you are using all the data point at every step might be expensive.
And if you're interested in this sort of thing, take 725, which is our optimization course, and we'll go into more detail than you could imagine.
Yeah. Yes, and I strongly recommend that course, actually.
Yeah,
it's a great course, yeah. Because, optimization is used everywhere in machine learning, so. All right. Okay, so some things actually, I might even skip that, but you can think about like we said we'll take a small step in the direction of the gradient, how large or small that step should be. That has effect in terms of the convergence, as you can see, right? So depending on where you start, if you're taking big steps, you converge faster to the minimizer in this case because it's a bowl, not inverted bowl, right? But you might get a larger residual error. You might not be able to hit the minimum exactly. Whereas if you take small steps, then your convergence is slow, but you can get closer to the optimum, to the minimizer. So there's a trade-off there in terms of what you should set the step size to. And again, there is a lot of more detail, which you'll learn in 725, right?
725.
Yeah, 725, right. If you take that optimization course on how to set eta and so on. All right. So let's quickly talk about, and you'll explore actually this connection in the homework. I just briefly wanted to mention the connection between Gaussian naive Bayes versus logistic regression. So we saw that if we assume, so Gaussian naive Bayes has a certain set of parameters, right? And we saw that it leads to a linear decision boundary under some settings, right? Do people remember when? When does Gaussian naive Bayes lead to a linear decision boundary? Equal class conditional variances, right? So if for each class, the covariance of your different features is the same, then you get a linear decision boundary. So you can think of, there's a set of parameters here, and there's a set of parameters for logistic regression. And is there any connection if at least in the equal class conditional case, they're both learning a decision boundary, how might they be related? And you'll explore this in more detail in the homework. Let me just mention a few points about it. That there is this representation equivalence. Of course, you should remember that it's only in the case where you have class independent variances, as we just discussed. Moreover, the solution you expect from both is actually not going to be the same because likelihood ratio, logistic regression makes no assumption about P of x given y, right? We did not assume any model for it. So they're assuming different models. They're learning parameters that are both maybe, specifying a linear decision boundary, but your solutions could be, of how the linear decision boundary looks like could be very different because of the assumptions involved, right? And moreover, they are actually optimizing different functions, which is a result of whatever model you assumed, the maximum likelihood estimate versus the maximum conditional likelihood estimate. Right? All right. Let me also say that I think we have a pointer. If not, I'll add one to this paper, which goes into more detail about generative versus discriminative philosophy. And here's like an upshot of what that paper says, that at least suppose we have infinite amount of training data, right? So lots and lots of data points. And we learn both something like a generative naive Bayes classifier and a discriminative like logistic regression. Then in the limit, as you have lots and lots of data, you expect both to perform the same provided your conditional independence assumption holds, right? Because that's what naive Bayes assumes. But logistic regression does not make any such conditional independence assumptions, as we saw, right? In fact, there's no model for P of x given y we assumed, and in particular, we did not assume that it factorizes into anything, right? So in general, you expect that when that conditional independence assumption does not hold, then discriminative can get you a better error than the naive Bayes, right? Because it's making stronger assumptions. Make sense? So why did we talk about in the infinite data case this happens? Because when we have finite data, we also have to think about how many parameters we are learning and how we are learning them. Okay? So let's think about the logistic regression case. We have d plus 1 parameters, and we are using all our data to learn all the weights simultaneously, right? Now let's think about, say, Gaussian naive Bayes. You have, what are the parameters there? You have the class prior. And for every class, you're assuming a Gaussian distribution. So for every class, you have a mean and a covariance matrix. And in fact, because of the conditional independence assumption, you have a mean and a variance for each feature. Okay? Again, if you do the online questions and you do the homework, you'll become experts at this. But essentially, you have a set of parameters for each feature. And because the distribution factorizes, you can learn all of those parameters completely independent of each other. You're using all the training data to learn the mean and the variance for one class. You're using all the training data to learn the mean and variance of another feature. Sorry, different features, not just different classes, I meant. Right? So for one feature, you have a mean and a variance. Another feature, you have mean and variance. And you can use all your training data to learn the parameters for each feature independently. Whereas here, you are learning this set of d parameters, which correspond to the d different features simultaneously, right? So a consequence of that is that, and as was shown in this paper, is that if we talk about finite data, and we talk about given finite data, what's the error you can get, and how that compares to the error when you have infinitely many data, then you will see that there's this extra terms that they characterized. And essentially, this one is larger than this. So what it says is that the discriminative approach, the error based on n data points is further away than the error based on infinite data points, right? Because you have a larger term here. Whereas for generative classifiers, these two tend to be closer because this is smaller. And really why that's happening is because your parameter estimates are coupled in logistic regression, and they are completely uncoupled in naive Bayes. So you can sort of hope to learn them in a statistically more efficient manner. You're using all the data to learn each parameter, whereas here you're using all the data to learn all of them simultaneously.
So why do we have a less than thing?
Why do you?
We have a less than but not?
So it's hard to prove the other bounds, though they do exist. So in this paper, they actually show, I'll have to go back and check, but I think they only show upper bounds. But that's just saying that It is an upper bound, but yeah, I guess you just have to take my word that it is tight. Yeah,
So
without.
the reason it's harder to prove is that it wouldn't be equal to that for all classifiers. Imagine a classifier that ignores its data, right? Then the epsilon discrete n and epsilon discrete infinity are equal. And so they don't differ by root d over n. So you have to make some assumptions on the classifier in order to get the maximum lower bound.
So we'll talk about these type of results more when we do theory, which we'll do in at least 2 lectures in the class. And you will see why bounds of this form arise. And at least they'll all be upper bounds to say how far is this from this. But the reverse, as I think Geoff explained it very nicely, that if you have a classifier that throws away your data, then these two are the same. So the lower bound is actually does not look the same. Yeah.
Sorry, is epsilon a normalized error with respect to the number of data points that we are considering?
Yes.
Okay.
That's why you see that as you get more data points, the error actually decreases. Yeah. So if you're thinking of this is like misclassification rate, right? So probability that a new point, or you can write it as like 1 over n times, if you want to write the empirical version, sum over all data points that you get the label right or not. So it's not the total number of errors you make, but it's the relative number. Yeah. Any other questions? So again, you'll explore this a little bit more in the homework, so I don't want to spend too much time on it, but I wanted to explain why they were able to show results like this and what's the significance of that. That the error here is far further away for discriminative classifiers like logistic regression from the error with infinitely many data points than it is for the naive Bayes kind of classifier. And the reason is this, that the parameter estimates are coupled in one case and not coupled in the other. So it's easier to learn. And so I guess that's sort of the summary of their paper to say that both of the logistic regression and naive Bayes learn a decision boundary. Naive Bayes makes more restrictive assumptions because it assumes that the features are conditionally independent given the class, and it has a higher asymptotic error, right? So because it's making a stronger assumption, in the limit of infinite data, it may actually perform worse, but it converges faster to its less accurate asymptotic error. And actually, this will become clear. Let me show you some of the figures they had in their paper. So here are a bunch of data sets they looked at. And the solid line here represents naive Bayes, and the dotted line represents logistic regression for each data set. And they have many, many more examples in the paper. But you see that it's usually the case that naive Bayes is converging faster. So this is versus number of data points, error versus number of data points. And naive Bayes, you'll see, is converging faster, but asymptotically, it has higher error than logistic regression. Right? And you see that happening in almost all the scenarios except for these two. In all of these 4 scenarios, it happens. In fact, they have many, many more examples in class. Yeah.
What step size do they choose? Or was it dependent?
This is after optimization.
Yeah.
So this is once you find the minimum on the training set.
Right.
And then test on a test set.
Right. So this is the test error, not just the training error. Yeah. That's important. Right. So yeah, in these 2 cases, why did naive Bayes do better? Any guesses? Yeah, probably the conditional independence assumption holds in these cases. That's why naive Bayes can actually do better. All right, so let me just end here about logistic regression, that it's a linear classifier. It goes after this different idea that because the decision rule is just decided by P of y given x, let's directly try to assume a model for that. Perceptrons do the same thing, which Geoff will go back to. And you should think about like and you'll explore it in the homework about the connection between Gaussian naive Bayes and when it's equivalent to logistic regression. And the thing we talked about right now about convergence rates, which converges faster than the other, and the reason being whether the estimates are coupled or not. Okay? Yeah.
Could a logistic regression handle situations like that? Why it's not binary? It can be 3 classes, 4 classes.
Right. So that's again something you'll explore in the homework. How do you do multi-class logistic regression? Right.
Step by step.
So you can assume a form for the different, how many, first of all, so you want to assume something about P of y given x. Here it suffices to just assume something for P of y is 1 because P of y is 0 is implied. Now when you're doing k classes, you'll need to assume a form for k minus 1 of them essentially, right? And work with that. Yeah. And this is something you'll do in the homework, and you'll derive what the gradient update rule will be for that case. Actually, another thing I wanted to mention was we talked about maximizing the conditional likelihood. And for naive Bayes, we also talked about doing the maximum a posteriori estimate, right? Because maximum likelihood estimates are sometimes, when you don't have enough data, are not as reliable. You can do something similar here. And again, I think in the recitation, Nicole will talk a little bit about that as well. So you can just change the objective here instead of doing, actually I have it here. So instead of doing maximizing log of just P of y given x, right? This is the likelihood. You can throw in a prior term, multiply this with the prior, but now the prior is on the parameters, which are w in this case. So you can try to maximize the product of the two. And you can see by assuming a particular form for the prior, you can get a different update rule. And why would you want to use different priors? Because maybe you want to bias your weights to be small and not large. And you should think about why you might want your weights to be large or small. What's the effect on the decision boundary? Okay, so maybe these are some of the issues you can think about and then go to the recitation to see the answers. All right, Geoff, you can take over. So you don't need this, right? Okay.
So, all right, is the level okay for me? Yes, okay. So, all right, back now to perceptrons. So if you remember at the end of last class, we were talking about the definition of a margin. And a couple of people pointed out after class that in fact, I had written something wrong, so I wrote cosine of theta as, so let me define first, right? So we have the margin was defined as this form here, right? The gamma as the maximum overall weight vectors of length 1, of the minimum overall data points, of the signed data point, ui, times dot product with w. Right, and so if you write on this, figure, right, if you define an angle phi here and an angle theta here, right, then ui dot w is not cosine theta; it's actually cosine of phi, right? And if you remember from geometry in high school, that is the same as sine of theta, right? So I should have said sine theta, right, instead of cosine theta. And what that means is that, well, sine theta is this distance, right? It's the distance from the example to the margin. And so you're finding the example that has the minimum distance to the decision boundary, right? All right, so at this point, I should say that well, that's interesting. Cool. All right. New technology. Sorry about that. So I apparently just, what did I do? All right, apparently technology is going to beat me today. So I'll fix this in the notes. But the margin is defined as the closest example to the decision boundary, assuming your weights are normalized to have length 1 and your examples are normalized to have length 1. Right? All right. So we're going to need later today an equivalent definition of margin. So that is if you solve this optimization problem here, that also gets you the exact same definition of margin. And I'll show you that in a second. But the idea is instead of fixing the length of W and optimizing the dot product, we're going to fix what the dot product has to be and optimize the length of W, right? And so scaling W is the same as scaling how big the margin has to be. So we can show that precisely this way. So this optimization here, that's the same as saying that we're going to minimize the, I'll introduce a new variable, capital W, subject to the constraints that, well, UI dot W is bigger than or equal to 1, just like this constraint there, but also that W is bigger than or equal to the norm of W, right? That's clearly the same as minimizing the norm of W, right? I just said capital W is bigger than the norm of W and minimize capital W instead. All right, so now I'll divide through by capital W, right? So this constraint is UI dot W over capital W has to be bigger than or equal to 1 over capital W, right? And then 1 is greater than or equal to the norm of W over capital W, right? And so now I'm going to define a new variable V, which is equal to W over the norm, capital W, the norm of W, right? And so now I have minimize W. So the variables are now, right, so here they were little w and big W. Now they're V and big W. And I'm going to minimize UI dot V bigger than or equal to 1 over capital W, and 1 is bigger than or equal to the norm of V, right? And then also I can define gamma to be equal to 1 over big W, right? So gamma is going to wind up being our margin. And so now we want to minimize. The variables are now going to be V and gamma. 1 over gamma, 1 over gamma, subject to UI dot V is bigger than or equal to gamma, and 1 bigger than or equal to the norm of V, right? And now minimizing 1 over gamma is the same as max gamma subject to these same constraints here, right? And so now that's the definition of margin that we had on the previous slide, right? So, all right, all right, apparently. All right. Apparently, I need to practice with my technology better. So this last optimization problem, right? We're finding the largest gamma subject to these constraints, right? So the largest gamma. Suppose that U1.V were a half and U2.V were a quarter, and we maximize gamma subject to gamma being less than both a half and a quarter. Right, we would get that gamma was the smaller of those two things, right? We get gamma as a quarter, and so we would wind up getting what is happening here? We would wind up getting that here, right? We wind up getting that gamma is equal to the minimum over all training examples I of UI dot V, right? So just like before, we're selecting out the training example that is closest to the margin, and then we're finding the V that is maximizing that possible distance, right? So I have now an equivalent definition of the margin, and this is nice because now I can work with constraints, a fixed set of constraints, ui.w bigger than or equal to 1, and then the length of w is going to wind up telling me the margin, right? The bigger w is, the smaller the margin, and the smaller w is, the bigger the margin, right? That makes sense to everybody? All right. So, all right. So, with that definition, we can now actually do the proof that the perceptron works. So, why am I showing you this proof? There's a couple different reasons. One is the proof is nice and simple, so it's nice to just give you an example of a complete worked proof of a machine learning algorithm. The other is that this form of proof, I'll talk about this more in a slide or two, is a form that comes up all over the place. It's a form called amortized analysis. So I'll show you that in just a sec. But for now, let's just do the analysis of the perceptron. And we're going to start with the analysis of the completely linearly separable case, right? So the margin is strictly positive. So what does the margin strictly positive mean? That means that we have, there's some W star, optimal weight vector, which has some norm, but it satisfies ui.w star is bigger than or equal to 1 for all examples, right? In other words, the margin is 1 over the norm of W star. That's what I just showed on the last slide. And let's say that we've normalized so that all of your training examples have norm 1, like in the previous slides. And so now we're going to do an analysis of the perceptron algorithm, right? So the perceptron algorithm, on every mistake, right, the form of the perceptron algorithm is, on a mistake, we have W gets W plus UI, right? And so now let's try and analyze that. So we'll split into two cases because there's two different kinds of updates the perceptron can make. The first case is when we make a mistake. So on a mistake, we're going to analyze a couple of quantities that look at least like they have some chance of being related to the performance of the algorithm. And when we put them together, it'll turn out that they let us prove some bounds. So the first quantity, the two quantities we're going to analyze, one is the norm of W, and the other one is W dot W star. Okay, why would we care about those two? Why would we care about those two quantities? Well, so the norm of W corresponds to the margin that we're getting, right? Or that we're trying to get. And W dot W star, well, if it's small, right, we're pointing away from the optimal direction. And if it's big, we're pointing toward the optimal direction, right? So we'd like the norm of W to be small, and we'd like W dot W star to be big. Right? And so we're going to try and prove that they remain that way or that they become that way over the course of the algorithm. All right, so on a mistake, we'll have W, so the new W will be, so we'll have W new dot W star, right? And that's going to be equal to, well, the new W is the old W plus UI dot W star, right? And so that's equal to W dot W star plus UI dot W star, right? That makes sense. And on our assumptions, right, we know that ui.w star is bigger than 1 all of the time, right? So this then is greater than or equal to w dot w star plus 1, right? So on every time we make a mistake, w dot w star grows by 1, right? And in every time we don't make a mistake, w doesn't change, w star doesn't change, so w dot w star also doesn't change, right? So after m mistakes, we have w dot w star is bigger than or equal to m, right? So that's nice, right? We wanted w dot w star to be big, and we proved a bound on how quickly it has to grow, right? Every time we make a mistake, it grows a little bit more, and because then we're pointing towards w star a little bit more, we're hoping that that makes it harder for us to have a mistake in the future, all right? All right, so let's look at the other one. The norm of w nu, right? Actually, let's look at the norm squared of w nu, because that's going to wind up being easier to work with. That's equal to w plus ui dot w plus ui. If we make a mistake, at least that's what it's equal to, right? Which is equal to w dot w plus 2 ui dot w plus ui dot ui, right? That's just expanding the square. We know that ui dot ui is less than or equal to 1 because we normalized all of our examples to have norm less than or equal to 1. And we know that ui dot w is less than or equal to 0 because we made a mistake, right? So in other words, we make a mistake, right? We classify an example correctly when ui.w is positive. We classify it wrong when ui.w is negative, right? And so, right, this term here is less than or equal to 0. And so the whole thing is less than or equal to the norm squared of w plus 1, right? And again, w doesn't change if we don't make a mistake. So after m mistakes, we have that the norm of w squared is less than or equal to m, right? So that's also after m mistakes. All right. So that's some pretty straightforward algebra. Now what happens when we compare them, right? So let's see. We have from this one, right, m is less than or equal to w dot w star, right? And that's less than or equal to the norm of w times the norm of w star, right? That's the Cauchy-Schwarz inequality, right? And so now we have a bound on the norm of w, right? From here, the norm of w is less than the square root of m, less than or equal to the square root of m. So then this here winds up being less than or equal to the square root of m times the norm of w star, right? So now we have that m over here is less than the square root of m times w star, right? We put that together and we get that the square root of m is less than or equal to the norm of w star, right? Or m is less than or equal to capital W squared, right? So what does that mean? So 1 over w is the 1 over capital W is our margin, right? So what this is saying then is that m is less than or equal to 1 over the margin squared, right? So if you have a very small margin, 1 over the margin squared could be a big number. You could make a lot of mistakes. If you have a very big margin, 1 over margin squared is going to be a pretty small number, and you'll be limited to a small number of mistakes, right? So does everybody follow the proof? Good, I see a bunch of nods. And so it's really kind of cool that on a single slide here, right, we're able to do the entire perceptron proof. And so, and that it comes out with a pretty simple answer, right? The number of mistakes that you make is pretty much exactly described by how big a margin you have. If you have a big margin, you'll converge very quickly. If you have a small margin, you might make a few more mistakes. But whatever the margin is, as long as it's positive, you'll make a bounded number of mistakes, right? And let me emphasize again that it's independent of what the dimension is of your problem, right? Nowhere did I say that there was that your examples had d dimensions in them. Didn't make any assumptions about that anywhere. So, so that's cool. So let me then say a little bit more about amortized analysis. So what is amortized analysis? Well, we want to bound the number of mistakes that the perceptron makes, right? Now, for any one trial, it's hard to get a non-trivial bound, right? I can say I make fewer than one mistake every trial, but that's not all that interesting a statement. Means I do better than getting all of the training examples wrong. So what we're going to try and do is an amortized analysis that instead of bounding things on one trial, it says that every time we make a mistake, it's going to make it a little harder to make a mistake in the future, right? So in this case, intuitively, what that means is every time we make a mistake, we point a little bit more in the direction of the optimal weight vector, and so we're less likely to make mistakes in the future, right? And so the way you do that is you pick what's called a potential function. And so in our case, the potential function combined those two quantities I was mentioning on the last slide. It was the norm of W minus W dot W star over the norm of W star, right? And we put bounds on Qi, right? So it's not hard to see that Qi is bigger than or equal to 0. Why is that true? Well, Cauchy-Schwarz again. W dot W star is less than or equal to the norm of W times the norm of W star, right? And so W dot W star over capital W, right? These two things cancel out, right? And so this term on the right is less than or equal to the norm of W, which is the term on the left, right? And so you subtract norm of W from norm of W, you get 0. All right? So that was the bound on one side. You can make an upper bound on Q as well, right? So I'm not going to prove it again, but the bound we proved on the previous slide, just putting things together, was that Q is less than or equal to the square root of m minus m over W, right? So m was the number of mistakes, W was the norm of W star. And then you can see that in order for this thing to be bigger than or equal to 0, we had to have a bound on the number of mistakes, right? Because square root of m grows at one rate. M grows at a much faster rate than square root of m. And so if m gets too big, this term on the term on the right, this one here, will overtake this one here. And we'd get less than 0, which would be a contradiction. Right? And so the potential function, you can think of it as summarizing the state of the algorithm, the history of the algorithm, whether we're in sort of a good state or a bad state, right? And a good state means we're not going to make very many more mistakes in the future, and a bad state means we might still make a bunch more mistakes, right? So I think that's basically all we have time for with the proof of the perceptron algorithm. Do we have questions on the proof before we go? Yeah?
Just one question. What's that index I on the computer?
Oh, sorry. That index I is a typo. Zoop. There it goes. You didn't see anything? All right. Any other questions? All right. Thanks. See you guys on Monday.